in the group of Martín Plenio. And after that, he came back to Spain. He worked here in Madrid at CSIC, in the Institute of Fundamental Physics. And in 2016, he moved to Swansea University, where he stayed like 2 years, till 2018. And since Alejandro loves Madrid so much, he came back to the place where he did the PhD, to the Complutense, and he worked in the theoretical physics department. And currently, he is working in the IFT, the Institute of Theoretical Physics. Now, the stage is completely yours.
Okay. Thank you very much. ¿Puedo usar esto o puedo usar aquí? Vale. Para que no haya interferencias, ¿no? Apago. Okay, so good afternoon, everyone. It's a real pleasure to be here. It's actually quite amazing, like all the audience. This is much larger than in any other conference that I've been recently to. So it's pretty amazing to see so many young people interested in this field and how it's been growing since many years ago. So today I would like to talk about some work that is in the context of these quantum technologies and how to use them as quantum simulators, in particular simulators of lattice gauge theories. So this is work that is done in collaboration with some people outside the IFT. So actually, most of the people in my group, they're sitting in this row over there. What I will be talking about today is not about their work. I think that they're going to give talks here, present posters. So I decided that I would talk about something slightly different. So this is work in collaboration with an experimental group that is led by David Lucas in Oxford, which is a trapped ion group, doing trapped ion experiments, in particular for high precision quantum computing. But I somehow convinced them to look into some other physical effects. And this is also work done in collaboration with Enrico Domanti and Luigi Amico from the Catania University and the Technology Center in Abu Dhabi. So these are some references of the things I would like to cover. On top of that, this is a long effort, so we ended up doing these things, but actually there are like papers earlier on that I will comment as we move along. So since this is a very long talk, you know, you can interrupt me at any point, and actually we don't need to get to the very end. So if there are questions, I'm happy to try to answer them, and we can even use the Blackboard. But anyway, so the menu for today, how I decide to structure things is by motivating a bit why these devices can be useful for high energy physics, and then I will tell you a bit more about the particular ideas that we have with trapped ions, so how they work, and how you can use them to try to simulate toy models or very small scale models of C2 lattice gauge theories. The nice thing is that you have some tunability over the geometries of the lattice, so actually you can do it about just a single link, but you can also do it on a loop, and that allows you to have, you know, like phases and a run-of-one interference. So I will report on recent experiments that have shown for the first time that you can see this run-of-one interference in a theory where actually the gauge fields, it's not like a background magnetic flux, but this is a dynamical one. And finally, I will tell you a bit more about how you start now as a theorist, thinking about how to take these ingredients, combining them, and studying like more complicated lattice models, either like by interconnecting these loops and creating a sort of ladder or a C2 loop chain, or by going into something else that's called a C2 Kreutz ladder. So let's see if we get there. So here's the motivation. So the motivation is that we have these quantum devices that are highly, you know, if you think about them, they're isolated quantum many-body systems that we have a lot of control over them, right? So basically, the main question that people are trying to answer is whether we can use them to understand better problems, for instance, in high-energy physics or in quantum many-body physics in general, right? So the idea is that we control this system and we make them behave according to a theory that we're interested into, and a theory that is difficult to solve by classical means, right? So for instance, a particular instance where this can be useful is in quantum chromodynamics in QCD. So what I'm plotting here is like the phase diagram of QCD, which is highly conjectural, and I will tell you why. So basically on this axis, this is temperature. On this other axis, this is the chemical potential. So essentially what happens is that as you tune the chemical potential, you start exploring regimes where there is a finite density of the fundamental fermions of the theory, so Dirac fermions, in this case would be quarks coupled to gluons, right? And the problem is that when there is a finite density of fermions, the typical ways of understanding these quantum field theories, which is writing them on a Euclidean lattice and doing Monte Carlo sampling, it faces the same problem, and you cannot do numerics easily with classical computers. So basically, this axis over here, all of the faces that appear as you go to finite densities is not very clear. It's a bit conjecture. So we have, typically we think that there are, like the hadronic phases where we are used to, right? We don't see the quarks, but we see how they form mesons and other hadrons, right? From there can be like a deconfinement phase transition where, these individual entities, they become deconfined and you can see them in a sort of plasma, right? But actually there are other phases of matter, just as in normal materials, right? There might be like spontaneous symmetry breakings of some symmetries, and these form collective orderings, right, of this, what they call quark matter. So for instance, they're like the equivalent of superconducting pairing. So here, like the quarks, instead of being paired with an antiquark, they are paired by what they call a d-quark condensate or a d-fermion condensate. And there are like some, just as in superconductors, you can have some S-wave pairing or P-wave pairing or things like that. Here is the color degree of freedom of the quarks, what underlies this superconductivity, right? So these are conjecture phases, and we would like to understand them. But the problem is that we cannot do classical numerics, so the idea is that we would use a quantum simulator, right? So this field exploded a bit in 2012 when there were first European proposals on how to implement some of these gates theories using quantum devices, in particular ultra-cold atoms in optical lattices. From a different perspective, work in the US showed that actually the type of problems that you find naturally in physics that have some structure, like this, these quantum field theories, I tried to put them on a lattice, so I discretize them. And even if you take the simplest one, which is a scalar field theory with 5 to the 4 interactions, what the group of Preskill did was to show that when you want to understand real-time dynamics, such as scattering in this field theory, and really reproduce real-time evolution, which is another problem where these quantum Monte Carlo methods do not work. This is actually a problem that is as complicated. It lies in the same complexity class basically as factoring prime numbers. So it's you can imagine that from the complexity classes of quantum problems, it's a very hard problem. So solving it with a quantum computer would mean that actually you are beating. It's a clear example of quantum advantage. So these are some previews in case you're interested into. Now the problem obviously is that these field theories with local symmetries, with gauge symmetries, they are very complicated. So we want to eventually simulate QCD in 3+1 dimensions. So this is a gauge theory with non-abelian local gauge symmetries, and this is very complicated. So it has the theories that underlie these models. They require a lot of resources. And we are actually over here, right? So we want to understand these theories, but starting with our devices in atomic, molecular, and optical physics. So the main message is that there is a long path to get there, but actually you don't need to go directly to the fully fledged QCD. You can go to other toy models in reduced space-time dimensions or working with other gauge groups and things like that. And still, in going there, you can hit on several milestones of the typical phenomena that you find in these non-abelian gauge theories, right? So you can start playing with your devices to implement local symmetries. Then you can, find instances of asymptotic freedom, of, chiral symmetry breaking, solitons, I don't know, all of these things that you would find in this gauge theory. This is actually like a two-way road because it's super complex to go from these AMO platforms that realize quantum computers or quantum simulators up to gauge theories, but actually there is now people that were doing lattice gauge theories with classical devices, with classical computers that now are getting interested into using these quantum computers, right? So if you actually want to understand how the system work and behave in order to understand better what are the prospects of these quantum simulators, there are so many things that are very technical and you need to understand in order to make these systems work, right? So the only thing I want to convey is that this is a highly interdisciplinary approach and everyone needs everyone in a sense. So what I will be talking today is what I was saying. So let's not be so crazy and try to simulate the full QCD, but let's go to a toy model, right? And in these toy models, the things that I will be talking about today, you can see local symmetries at play. You can see, again, non-perturbative physics. Well, this dynamical mass generation, it will only be talked at the very end, and solitons as well. But the thing that you will see, and you will grasp is that of confinement, right? So the fact that these quarks are confined into these hadrons, it will have toy manifestations in small-scale quantum simulators that are based on these AMO systems. Okay, so the first thing that comes to mind when you think about using these quantum devices for, to explore models of physics is actually to use current devices that you can access on the cloud, right? So for instance, we have this small scale or intermediate scale quantum computers, and actually they can be used to realize several algorithms. These algorithms are performed by doing gates, but the kind of algorithm that you're interested as a physicist is that of understanding a real-time evolution of a physical problem, right? So I encode the model that I'm interested in a certain Hamiltonian, for instance. I know that time evolution is described by this full unitary, if the model is time independent. And then what I have, my resources, are a set of unitaries that lie in the universal gate set of my quantum computer, right? So I can do like 1 qubit gates over any qubit in the register, or I can take 2 pairs, depending on the connectivity of the computer, 2 pairs of qubits and perform an entangling gate, right? And now the idea is that I have this set of many different types of 1 and 2 qubit gates. It's an extensive because they have to be over all possible pairs in the system, right? And I will apply a number of them. The idea is that when I concatenate these gates, if the number of gates that I'm using and I'm careful enough on how I concatenate them, I will be able to reproduce an effective unitary that is similar to the one that I'm interested into, right? So this breakdown of products of unitaries into the full unitary I'm interested into, this is the Trotter decomposition. So there are well-known schemes that you can follow in order to simulate the physics that you are interested into, right? The problem with this approach is that when you go to the real numbers of what things, the resources that would be needed in order to address problems that are meaningful, even if they are much simpler than these gates theories. For instance, you might be interested in just understanding what is the physics of strongly correlated spin models in a certain lattice. This is much closer to the device, the degrees of freedom here, which are qubits, right? When you go into the resources, what you find out is that actually, the number of qubits that you would need lies on the order of, in between a few hundreds and 1,000 qubits, and the number of gates that you would need to apply lies on the order of 10 to the 8 or so, 10 to the 7, 10 to the 6, or 10 to the 8 gates, right? And this is assuming that all of these gates, they are perfect, right? This is just the error that would come from this trotterization or from the requirements of your problems being meaningful, right? So even if these kind of physical problems have a lot of structure and the resources you see, they lie on the bottom corner here, so they are the less demanding resources. If you compare to other problems that quantum computers can solve, it is still far away from what current technologies can do. And in fact, when you go and instead of think about spin models, you think about gates theories. You could think about one of the simplest gates theories, which is quantum electrodynamics. And now instead of 3 + 1, you put it on a line, right, on a lattice, on a single chain. Then basically, there are estimates that tell you that if you follow this digital approach to quantum simulators, what you would need is gates on the order of 10 to the 5 or 10 to the 13 gates, right? So this means that, if these gates are noisy, I need to account for errors that are lower than 10 to the -10 or 10 to the -13, right? And these are things that you cannot do unless you do quantum error correction. So there is an additional overhead because I cannot just use bare physical qubits, right? So my problems, they will actually lie over here. I need more gates, maybe the same number of qubits, right? But these qubits, they cannot be physical qubits because I cannot reach those accuracies in my gates, right? So there is an additional overhead in quantum error correction. And here, for instance, I'm taking some estimates of Cesar. They are even simplified, but what you can see here is that these unitary gates, they are not perfect unitaries. They are subjected to errors. So typically, what I do is that these unitaries, they are the ideal unitary, but they are followed by some quantum channel that represent the noise, right? And my noise, it's characterized by a single number, which is the error rate. Typically, people consider like a depolarizing channel. So I have the perfect unitary, and it's followed by some errors that tend to shrink in all directions isotropically the Bloch sphere of my qubits, right? So what you find out here, for instance, when the physical error rate, so the error rate per gate is on the order of 10 to the -3 or slightly above. These are the numbers that nowadays you see in these cloud quantum computers. Essentially, if you want to build a quantum error correction code that can do, I don't remember here, I think that you want to reach logical errors that are 10 to the minus 4, or I don't remember if it was 10 to the minus 6 or something like that. So you want to have protection. So you have physical errors that are 10 to the minus 3. You want to reach a logical error which is on the order of 10 to the minus 4 or 10 to the minus 6, right? And that means that the overhead here, the number of physical qubits that you would need, lies between 1,000 and 10,000, right? So this means that there's a huge overhead. It's not that you can go ahead with just 100 qubits, but you will need several hundreds and several thousands, right? It's very important, actually, to be below what we know as the quantum error correction threshold. So these are these lines over here that you see. Essentially, for the different quantum error correction codes that you use, you will find a different threshold, and you have to be below. And that means that as I decrease the physical error of my gates, right, I am exponentially decreasing the number of qubits that I need to reach a precise logical error, right? So you see that if I'm well below the threshold over here, then instead of needing 10 to the 3, I will need 100 qubits per logical qubit or something like that. So in spite of that, there are now NISQ devices that people are using, and instead of using quantum error correction, they are using other techniques such as quantum error mitigation and so on. And you start seeing that they can still hint at what is the physics of the complicated lattice gate theory or things like that. I will not cover that today, so I just want to mention that this quantum error correction is not the only way forth. We believe that this is the only way that is scalable, but in the current technologies, if you use quantum error mitigation or quantum error suppression and things like that, you can still carry on for a while and get meaningful results. The other thing I want to talk, or the thing I want to focus in is, instead of concatenating gates that are noisy, I want to think about having, instead of reproducing just the unitary by concatenating gates, I want to reproduce the Hamiltonian of the model I'm interested into in the system that I have control over, right? So the kind of pictorial way of thinking about it is I will not use this device as a black box with a number of gates that I can concatenate, but I will open the door, right, and see what is inside. So inside is an AMO system that is, many-body quantum system. I have a lot of understanding of it at the microscopic level, so there will be a bunch of microscopic parameters that I can control experimentally via lasers or whatnot. And the idea is that when I tune this set of coupling strength to a particular regime that I have to think about how to do it, then the system behaves according to an effective Hamiltonian that is very close to the model I'm interested in, right? So when you look at one of these quantum computers, for instance, this one that is made of trapped ions, then the question is, what are when you open the door, what is inside, right? It's not just qubits, it's actually charged particles. And I will try to show this video here, which I think is super nice. This is not the kind of traps that they use in the lab, as you can imagine, but these are, okay, these are very simplified. So the idea is that you connect a certain conducting material to a signal, right? So it will not be a DC potential, but an AC potential, and it creates an electric field inside, and now you have charged particles that react to this field. So when you have a bunch of them, they repel each other on the one hand because they are charged, but then on the other hand, they are confined by this effective electric potential, and they form crystals. So essentially, these crystals, they are very similar to the ones that we see in solids. The only thing is that they are constantly driven, right? So as you see here, on top of whatever vibrations, collective vibrations of the crystal, actually they are responding to the driven fields that I'm applying through this conducting material, right? So this is what is inside. Instead of having dust particles that are charged, what we have is really quantum mechanical particles that, on top of moving and collectively, when I cool them down, this will give rise to quantized vibrations, so phonons. On top of that, each of them has an internal level structure, so an atomic level structure, and I can use it to encode quantum information or to treat it as qubits, right, or spins. So that's what we have, and then we have to learn how to play with it, right? So the question is how you describe it microscopically and how you find schemes. It's not just doing Trotter evolution, but you have to be more physical in thinking about how to bring the system to a particular regime where your effective Hamiltonian is the one that you want to simulate, right? And now it comes a bit, the modeling of a physicist of these systems. As you see, they appear from dust particles down to atomic or molecular systems that are ionized, and then they repel each other, and they are subjected to an oscillating electric field. This is a beautiful system with many different complexities, but actually the job of a physicist is to simplify as much as possible, right? So basically, out of all the complexity of nature, we try to come up with simplified theories, and this is kind of, if you think about it, is a really piece of art, and the simpler it is, the better, right? So in all these theories like Maxwell electrodynamics and whatnot, they are super simple for the kind of complexity that they describe, right? So we are aiming at something similar. So we have these highly technological devices, right, which are composed not of clips, but really microfabricated structures that are, segmented electrodes subjected to, DC and AC potentials. They might be, there might be like integrated optics that allows for lasers to come in and shine into the position of my ions, right? And at the end of the day, what they create is like beautiful crystalline structures of ordered charged particles, right, trapped ions. And what we want to do is to simplify this to the level where it becomes kind of a piece of art. But actually, since we are not as good as Maxwell, was the kind of theories that, the kind of pieces of art that we can come up with, they are even too simplistic. So let's look at the simplest example. So I look at one of these, surface trap, microfabricated surface trap. I told you that there are a bunch of electrodes that are segmented, and I can subject them to signals, right, so that are controlled in my quantum computer, my trapped ion quantum computer. They are controlled by DC and AC potentials. And what they do at the end, they are fastly oscillating signals, and this is the reason why you saw these charged particles. They were moving at unison with the driving field. But when this driving field is super fast, it's on the order of radio frequencies, actually it's very good to think about the problem as if it was an effective, what they call a effective pseudo-potential, or ponderomorative. Well, I will not get it anyway. So it's like an static potential that comes out of the average of these highly oscillating forces. And in this case, what you find out is that by controlling these electrodes, what you can make is kind of a double well that confines the ions at different positions. So the typical distances are on the order of tens of micrometers. And what you would like to do is to understand what is the physics of this system. Obviously, since each of them is a charged particle, they will be coupled through Coulomb interaction. Now the key is that this Coulomb interaction and this effective potential, what makes them is to form a crystal. And now, as in solid-state theory, you consider like small fluctuations around the equilibrium position, and it turns out that the vibrations of the ions get coupled through each other through a kind of dipolar interaction, right? So basically, I have harmonic oscillators that I can assign to every single ion in my chain, right, or in whatever crystal I have. And through second-order Coulomb interaction, there is a kind of dipole-dipole interaction that couples the vibrations over here, the local vibrations over here, to the local vibrations in a different side of my chain, right? In particular, when the local curvature of this potential is much stronger than the coupling strength, it turns out that these vibrations, these quantized vibrations, which are like collective quasi-particles in a sense, and in a solid they are not conserved. There is not a conserved number of phonons typically. In these systems, they are conserved. So actually, you find effective theories that describe each local oscillation as a independent harmonic oscillator, and then these distant harmonic oscillators, they are coupled to each other through a tight binding model that is controlled by a dipolar coupling strength. But the important thing is that whenever I destroy a phonon over here, it jumps somewhere else, so I create it over there, right? So there's a global U1 symmetry, so that I can start thinking about these phonons as particles, right? Real particles that have an entity and their number is conserved. Very good. So this is still very far from what I'm aiming for, because these particles actually, they are collective vibrations. And if you think about the phonons, they do not respond to external gauge fields as charged particles, as electrons, for instance. So if I want to use this in order to simulate a gauge theory such as quantum electrodynamics, I'm still missing a lot, right? So one thing that we did some time ago is to think about how you can engineer schemes to control this tunneling effect. So you know that when charged particles move from one part to the other under under an external gauge field, they pick up a phase, right? And if they actually go around a solenoid, it will be a run-of-Born effect. So this is translated in tunneling strengths that have the effect of this background gauge field. So the first thing we did was thinking about how to make these phonons closer to a charged particle. Well, what you could do is try to effectively engineer this tunneling so that it resembles that of a charged particle in a background gauge field. So one thing you can do, and I will be quite brief here, is you can think about this tunneling, of particles wanting to tunnel to a neighboring site. It can be inhibited if you subject them to a bias, right? So there is an energetic bias, there is a gradient, such that when its phonon or its particle wants to tunnel to a neighboring site, it actually doesn't have the energy to tunnel there, right? So when the tunneling strength, now I call it T, before it was capital G, is much smaller than the gradient, I'm suppressing energetically these events, right? And now the idea is that I come up with a laser, which is depicted here by this moving, it's two lasers with a moving standing wave, and this brings me the energy to perform the tunneling. So I assist it again, right? So I want to tunnel from this energy towards that energy over there, and what I will do is I will start absorbing photons from the drive, and eventually I will hit the place where I'm going into, right? So this is nice because you assist the tunneling. What you are missing now is the other part of the story, that you are absorbing photons that come from a laser, so there is recoil. So every time I absorb a photon, my atom, or my phonon in this case, it feels that there is a conservation of linear momentum, right? So I start absorbing kicks from the lasers, and at the end of the day, there is a final recoil. So when you work out the details, and this is very easy math, what you find out is that under this periodic modulation, this is some kind of Floquet engineering, for those of you that have been working with that, there is an effective Hamiltonian where I get addressed tunneling strength. It's addressed by a Bessel function, but the important part is that I'm picking the phase of this recoil. And you can engineer things now such that if my particle goes around a closed loop in phase space, it picks a phase, which is just the line integral of an effective vector potential, right? Which is equivalent to sensing what would be a background magnetic field, and I have access to an effective run-of-Born effect, but now it's developed through the vibrational excitations of my trapped ion chain, right? So the particles are not even particles, they are phonons, right? But I'm making them behave as if they were charged and subjected to an external gauge field, right? So this actually worked out to a certain level in experiments. So here you can see some experiments in the group of Tobias Schatz. This is in collaboration with Diego Porras here from the Institute of Fundamental Physics, where they created such a triangular microfabricated surface trap which can hold 3 ions on top of it. So now it's like a purely 2D trap, and the ions, they sit on top and they form a triangular crystal, right? So what we were able to do by doing this Floquet engineering is essentially we would excite the 2 ions in blue and green. You excite them, they start to vibrate. But now you modulate the system, and the thing is that they want to tunnel to the orange ion, actually. But when they do so, there is an underlying run-of-Born phase, and when this phase is equal to pi, they no longer tunnel, right? So if the phase is phi, you start seeing periodic exchanges back and forth. But if it's on the order of pi, there is perfect interference, and you see that they do not tunnel coherently anymore. The only thing that you're seeing in these coherent oscillations, there is a damping or a heating, and in here as well. So this is the residual heating in these systems. There is a lot of electric field noise in this system. So because the ions are sitting very close to the surface, and what you're seeing here is that even if the flux is pi, there is a background signal due to the heating, but there is no longer this exchange. So this is why I say that this is realized to a certain level. In any case, whether this is satisfactory or not, the truth is that we are still very far away from what we wanted, right? So this is just what we just discussed, is making these phonons behave as charged particles under a background gauge field, but this gauge field doesn't have any dynamics, right? And we want to go to a pure gauge theories where the gauge fields are actually dynamical variables. So what we want to do at the end of the day is, this run-of-Born phase, this line integral, should now depend on time, but not externally. There should be like electric and magnetic fields that are time-dependent operators, if you want, and they should be controlled by their own Hamiltonian, right? the Hamiltonian of Maxwell electrodynamics, or if you want to go to a non-abelian gates theory, that of QCD or some other gates group, right? And this turns out to be quite complicated. So the simplest thing you could think about is, on top of reducing the dimensionality as much as possible, you can think about exploring some other groups, right? Instead of, I started from QCD, where it's a non-abelian group. Then I moved to quantum electrodynamics, which is abelian, but it's still continuous. It's U1. And now what I go is to a group which is the simplest one you can think of, which is a discrete group, right? So it's a C2 group. So now my gauge fields, they are the equivalent of these electric and magnetic fields, but actually I can represent them directly through spins or through qubits, right? So this is what people call in the literature an Ising gauge theory. And the key of this theory to be characterized as a gauge theory is that it has some local symmetry, right? So it has a simple Hamiltonian that is composed of two terms. So it's an electric field term, which is just the equivalent of a transverse field acting on sigma x operators of my qubits. And then I have a plaquette term that is an interaction of 4 qubits that live on a plaquette of my system. So basically, instead of living in the continuum, my fields are discretized on a lattice. They are discretized on a square lattice. They are qubits, and they live on the links of the lattice. The electric field, it just acts as they want the qubits to lie parallel to the x-axis, and the magnetic fields, what they're doing is that they're acting over plaquettes. So whenever I have 4, I don't know, where was it? Here. Whenever I have 4 qubits sitting on the same plaquette, there is a magnetic interaction that wants them to be aligned in the C direction in a collective fashion, right? So if you take some time to think about what is the local symmetry coming from, actually what you can find out is that there is an extensive number of operators that are the generators of these local symmetries that commute with your Hamiltonian, and they are what people call vertex operators. So they are products, again, of 4 x Paulis around every side of my lattice. And what you can see is that they always touch at most the plaquette operator of 4 Cs. They touch it at 2 sides, so that means that it commutes with C, but it also commutes with X, right? So I have, for any side of my lattice, I have operators that commute with the Hamiltonian, so they generate a local gauge symmetry. What it means in practice is that this dynamics led by this Hamiltonian, it cannot bring me out of a set of super selection sectors that are fixed by the eigenvalues of these operators. So basically my Hilbert space breaks into several sectors, and I pick one of them where the dynamics will take place. So typically what I do is that I stabilize the state to a +1 eigenstate of these Gauss operators, and this is the equivalent of what would be the Gauss law in quantum electrodynamics, right? So basically this is the part that it would be the gradient of the electric field, and this is the part that tells me that there is or there is not a charge density on the right side of particles, right? So this C2 gauge theory, in spite of looking very simple and very mild, it actually contains a lot of features in connection to this QCD. For instance, you can start modifying the microscopic parameters. Here is just this parameter small h, and what you find out is that there is a quantum phase transition from a phase that is confined, where this electric field is dominating, and then you go into a phase that is deconfined, where this plaquette dominates. So this is a phase that actually is connected to topological order, and is also connected to this quantum error correction I was telling you before, right? So there are non-local observables related to essentially Wilson loops. So it's just products of like these linear integrals that I was telling you before. So there are like Wilson loops that either scale with the perimeter or either with the perimeter or with the area of that is enclosed inside them, and this tells you whether you're in a confined or a deconfined phase. So we would like to do that because it's the simplest gauge theory. You would like to implement this on a trapped ion system, but actually what happens is that even if this is a mild-looking Hamiltonian, it contains 4-body interactions, and these are very difficult to implement if you think about the Hamiltonian itself, right? So typically what we have is interactions that are mediated by photons or by phonons in superconductors, and they're typically 2-body, right? So it's not 4-body interactions. So this is a bottleneck. In all these analog quantum simulators, it's very difficult to engineer these things. So what you can do instead is, okay, let's just, this is a toy model in any case. So maybe if instead of looking at gates variables, gates fields, which are described by these qubits, if I introduce matter also, there will be an interplay, and I can still find deconfined phases in my model, even if they are not driven by these placket terms, right? And I will try to convince you that this is possible. So when you include matter into the model, now there is a different manifestation of this deconfinement. I was telling you that this is when you only have gates degrees of freedom. People talk about Wilson loops and how they scale with the perimeter or the area of the enclosed by the loop, right? Now when you have matter, you have a more visual or more physical way of thinking about the confinement. Because basically, when you have matter, this matter acts as a source or as a sink of electric fields, right, of these C2 fields. So actually, we'll enter in the right part of the Gauss law, right? So this is the gradient of the electric field in a sense, and this would be the rho of my matter, right? So if I have a background Gates field, it modifies this Gauss law. And what you can prove actually is that when you are in this confined phase, when the electric field is very strong, two external particles, actually they are subjected, or they feel an effective linearly rising potential. So this is the confining string, right? So there is a string that connects any two C2 charges, and this string, when H is very strong, it has a very strong tension, so basically they cannot move apart. They're really tightly confined to each other. On the other hand, if I start loosening the electric field and I go below the critical point of the model, essentially the string is broken in a sense, and the potential becomes constant, right? So my string now can fluctuate, and these particles, they have space to move around. So this is the deconfined phase, right? So these are the kind of things that we are interested in to look in. What is the simplest model where you have C2 fields and Gates fields that can allow you to see this dynamically? Well, it's this simple C2 Gates theory on a chain. So basically what I have now is I'm thinking about my previous phonons. So I'm thinking about creation and annihilation operators of bosonic particles that want to tunnel from site I to site I+1, right? So this is what I was discussing before. I'm missing here like some capital J, which would be the tunneling. But now the new thing is that since they have to be charged, this tunneling has to be Gates invariant. So it has to be mediated by the Gates field. It would be like the exponential of the integral of the vector potential. Now in these C2 Gates theories, this is much simplified, and it's just the effect of a Pauli matrix of the Gates field that lives on the link, right? So I want a particle to tunnel from here to there. The only way that it can do so while respecting Gates symmetry is by mediating the tunneling by a Gates field, a Pauli matrix, right? So what you find is that this Hamiltonian still has an extensive number of conserved quantities, right? Or symmetry generators. You just have to modify, right? So before it was vertex operators around the site, right? So X and X, but now the sites, they're populated by matter. So the parity of the matter is what enters in this effective Gauss law, right? So it's again the equivalent. If I take this parity and I put it on the right side, it will be the equivalent of the gradient of the electric field equals rho of matter. And what I want to see now is, for instance, I start my initial state with two bosons sitting at two sides. I let the system evolve. Since this model has to be Gates invariant, my particles now, they have to act as, the Gauss law has to be fulfilled. So basically, this means that this particle has to generate an electric field that carries all the way until the other particle. So there is this electric field string, and I want to see how this, this pair of particles, how it evolves in time. So we did this with MPS, and you can find this type of confinement dynamics. The particles will start dispersing a bit, as if they were free particles, but eventually they get away too far, and they start seeing that they are connected through a string, so they recombine again. So this is the typical Vannier-Stark oscillations that you find in these confined phases, so where basically everything is due to this linearly rising potential. Okay, so how can we realize this with trapped ions? I was telling you before that we were using the phonons to behave as if they were charged particles under a background Gates field. Now what we need to do is still use them as if they are behaving as if they are charges, not anymore U1 charges, but C2 charges. And the remaining thing that we need to do is to use the other degree of freedom that we are so far not using to represent the Gates fields. So these are the qubits. So every ion has an internal level structure. I can encode in it a qubit, with it a qubit, and these qubits will play the role of these dynamical gauge fields that sit on the link of my lattice. So how do you do that in practice? And this is again going to this first slide I was telling you about, that you have to know the physics and come with schemes where I tune my parameters to a certain ideal point, and I engineer an effective Hamiltonian that resembles the theory I want to simulate, right? So if I think about one of these ion crystals, what you have in these ion crystals actually is that these vibrations, they can happen along any direction of my trap axis, right? So in particular, they could be longitudinal, but they can also be transverse along the x and the y direction. So this is what I'm depicting here in white and green. The thing is that they typically have different trap frequencies. So there is a trap frequency omega x and omega y for vibrations along this direction and this other direction. Now you can come with a laser, as we were doing before. We were using a laser that exerted these recoil effects. Now the effect of this laser will be slightly different, right? So this will act as some sort of parametric conversion, right? So a parametric converter that whenever the frequency of the laser exactly meets the difference in frequency of the two modes, it allows for the exchange of excitations between mode I and mode X, right? But now, since it's coming from a laser, you can tune it in a way that the internal state of the ion also enters into this parametric conversion, right? So this is essentially the scheme that we have with boards, and actually, if you apply some detuning to the lasers, it can play the role of the electric field of your theory, right? So this is, in a sense, what people in the community call synthetic dimensions, in the sense that you can actually do it either with a full change, but you could do it with a single ion, right? So here you see no index of the ion sitting on the chain. You could do it with a single ion, because in each ion is hosting two modes, right? The mode in X and the mode in Y. So this is like a synthetic link. I don't need these particles to be far apart. I'm creating a synthetic link by just driving the system correctly, and it is generating a gauge theory on a link, right? So this actually worked kind of well in the experiment, but there is a caveat that you have to think about, which is the fact that these systems are noisy, just as the quantum computers are noisy, and I was telling you that these unitaries are not perfect. Here in the analog quantum simulators is the same thing, right? So for instance, here at the Hamiltonian level, one type of error that typically appears in the experiments is like some fluctuating magnetic fields, that they add a Zeeman shift to my qubits that now fluctuates in time. So this is some random variable or some random process that acquires values and defaces my qubits. So the problem with this term over here is that actually it does no longer commute with the generators of my local symmetry, right? So if I think about it, I have a very large Hilbert space. I told you that these Gauss symmetries, they allow me to focus on a sector where all the physics should happen because there is gauge symmetry. Now, since this system is engineered, there are terms that break this symmetry, so they want to bring me out. So this is very similar to error correction. So there are defacing errors that bring me out somewhere else in the Hilbert space. What I could think about doing is, you measure something that doesn't affect the physics of your system, and you correct back to the physical space. This would be error correction. But this is kind of difficult because you would have to measure the stabilizers of your system that now involve, just X operators. This is easy, but you have to measure the parity of your phonons. So that's pretty easy. What we came up with is using some other techniques which are not directly measuring generators, but actually doing something actively, such as refocusing your system. At the end of the day, this is like defacing. I can use refocusing, a spin echo, in order to kill the effect of this magnetic field, right? But you directly see that if I do something only on my qubits, I do a pi pulse, and that refocuses this term over here, I'm also refocusing the tunneling that I want to induce, right? So what you have to do is a combined spin echo. So you have to, at the middle of your evolution, at the middle instant of your evolution, you invert the spin, but then at the same time, you have to change the phase of the coupling, right? This is this parametric resonator. So when you do so, you're picking this minus sign over here and that over there. You are not affecting the Hamiltonian that you wanted to simulate. You're just killing the part that induces the noise. And they did this in the lab, and actually it worked pretty well. So this is this figure that you can see over here. So here, what they are able to do in these trapped ion systems, right? So they can actually measure what is the population of the ion to be in a certain Fock state of these oscillators, either in direction X or direction Y. And they can as well measure what is the internal state of the qubit, right? So they can measure in any basis, projectively, they can measure in the C basis or in the X basis. So here in this plot here, what you see is that, so I'm starting the system to be, for instance, I put one phonon in one of the modes, right? And the magnetic field is pointing in, sorry, the qubit is pointing in this direction, so it's in a Hadamard plus state. And then due to this engineered evolution, the particle will want to tunnel to the left side, right? But if it does so, due to this Gauss law, the electric field has to follow, right? So if it was pointing in this direction, then it should be pointing in the other one. So what this is telling you is that there is a correlated dynamics, periodic dynamics of particles being exchanged between one side and the other, right? But since they are charged under this C2 gauge field, the gauge field follows periodically in the same way, right? So what you're seeing here is like a string in a sense, right? I have a string that is extending and then compressing, extending and compressing, and it's completely attached to my charged particle, right? And this is why these two things are correlated. And this is, it's a very small system. It's just a C2 link. But what we were able to prove is that actually you have a lot of resolution. These oscillations, they carry for quite a long time. And actually we were the first ones to measure like that this charged particle is correlated to the electric field. There were previous experiments in ultra-cold atoms that were not able to measure directly this electric field. How am I doing with time? Who's taking the time? Okay, so another thing you can start doing, and this goes to the direction of, maybe I don't have like this fully fledged QCD that is very complex, but now you can start doing things that people didn't think about because you have other degrees of freedom and other theories. In particular, what we have here is a theory where the fundamental matter is bosonic, and the gauge fields, they are just discrete C2 fields, right? The fact that it's bosonic is completely different from all these lattice gauge theories where you have at the end this like discretizations of Dirac fermions, right? And the fact that it's bosonic, it means that you can start piling a lot of bosons on top of each other, right? So you can create wave packets of bosons, and now you can start thinking about, what is the minimal wave packet that makes sense under this gauge theory. In particular, it has to be a wave packet that has a well-defined charge, right? So what you find is that the notion of charge in these C2 gauge theories is rather special. If I have one boson, this is charged. If I have two bosons, it's 1 + 1 modulo 2 is not charged, right? So the Hilbert space or the Fock space is broken into even parity and odd parity sectors. The even parity ones are not charged, and the odd parity ones, they have a single C2 charge, right? So the question is, now I don't want to be in a Fock state, which is either 0 or 1. This is what we did before. I want to be in a wave packet that belongs either to the even parity sector or to the odd parity sector, and therefore I can think about having a well-defined charge in phase space, right? How you do that? Well, this is a concept of the people studied in quantum optics a long time ago. Is just by thinking about squeeze states, right? So if I act on the vacuum of one of my modes with one of these squeezing operators with amplitude R, essentially what I'm doing is, you expand this exponential, and I'm always creating particles in pairs, right? So I have either the vacuum, 2 phonons, 4 phonons, and so on and so forth. So basically this wave packet in phase space over here, which is squeezed somehow, so I'm just not depicting it as a Gaussian, it is neutral. It doesn't have any charge because it's always composed of pairs of particles. If I do this squeezing, but instead of over the vacuum, I do it over a single Fock state, right, which I can create experimentally in these trapped ion systems, then you see that this is the superposition of 1 phonon, 3 phonons, 5 phonons. It's always carrying a charge of 1 under these C2 gauge theories, right? So this is what they were able to do in the lab also. And it also comes with, first of all, you would like to understand, now I have this C2 link, so I have a gauge field sitting in the link. Now I have maybe this squeeze state on one side and the vacuum in the other one. What is the dynamics, right? So what you expect is that somehow this whole wave packet, it tunnels to the neighboring side and it exchanges with the vacuum, right? But this brings another question, which is how am I going to probe these systems, right? Before I was able to measure projectively the qubit in the C basis or in the X basis, I was able to measure the number of phononic excitations in the trapped ions. How am I going to tell whether this squeeze state is tunneling and whether the electric field follows with it, right? Whether it has a string attached. So actually, there is another kind of interferometric scheme for measurement, which is very interesting when you look at it from a fundamentals perspective. It's measuring something that is similar to a generating functional in field theories, and it's called a characteristic function. So basically, what it does is it measures. So you take an ancillary qubit, you couple it somehow to your system, right? And then, sorry, the ancillary qubit is over here. This is my system. I couple it somehow to my system, and then I make a projective measurement. Out of this projective measurement, what I'm able to do is to recover the expectation value of a unitary operator, right? This is what in quantum computing people also call a Hadamard test, and in field theories they would call a kind of generating functional. So this characteristic function now, it lives in phase space directly. So it's, there are complex numbers which are just the position plus IP. These are just numbers that tell me where in phase space my wave packet is. And this characteristic function is telling me how this wave function spreads in phase space. In fact, if you Fourier transform this characteristic function, it gives you a quasi-probability distribution, which is called the Wigner function, and people used it in phase space methods, right? So this is the experiment now. So what you can see here is that they are starting the state in this squeeze state in one of the modes and the vacuum in the other one. Then they follow the evolution under this effective C2 gates theory. And what you find is that at the exchange period, essentially the vacuum has gone to the left side, and the squeeze state has gone to the right, but now it's rotated. So this is related also to the properties of these squeeze states. If you let the system move back after one full exchange, you will go back to the initial state. So you can start, as I said, being more creative and looking into things that are not considered to be a standard in lattice gate theories. The other thing you can think about is trying to grow in complexity and go away from this link. So the first thing you can think about, and that brings you close to 2D and to all this physics about this deconfinement and these placket operators and so on and so forth that I told you about in this C2 lattice gates theory, is to think about having a single loop that encloses an area that now has a magnetic flux in a sense, but this flux is dynamical. So the way of doing this in the lab now is, instead of considering a single ion that can have vibrations along Y and along X, so this would be the two sides over here, that by this parametric driving, you are able to tune a tunneling that depends on the qubit that sits on the link. So this would be sigma C. So I have a tunneling over this direction. This is with a single ion, but now I have two ions. So there is, for the other ion, there is another qubit that can mediate this tunneling. And I told you before that these distant ions, they are coupled through Coulomb interaction. So it's this Coulomb interaction to second order, which is a dipole term that builds a kind of tunneling between site I1 and site 2, right? So this is what would come naturally if I just apply my parametric driving protocol to two ions. I would get this effective synthetic dimension where two links of this square, they are gauge invariant, but the other two, they are not. So what we came up with is, now again tuning my microscopic parameters, what I can make is this tunneling strength over here, which is due to this Coulomb interaction to second order, can be much stronger than that one over there. So this means that these two modes over here, they hybridize, they become collective modes, for instance, the center of mass mode, right? Or this asymmetric mode, if you want to play with that one. What we played in the experiment is with the center of mass mode. So this is very strong. The two ions, they hybridize, they oscillate as a center of mass mode. And then what you have effectively is the tunneling of the center of mass mode from these two ions sitting over here to the other one in the other direction over there. And it can be mediated now by two gauge fields. It's not just one qubit, we have two qubits, right? So we now have two links, one of them on the left and one of them on the right. And this, even if it looks very trivial, it actually encloses this idea of having a plaquette in between. If I have an excitation that travels this way and picks a phase, it can interfere with the excitation traveling this way and picking a phase. So there is a Aharonov-Bohm interference. What we discovered when doing these calculations, which are not very difficult, but you never think about these things beforehand, you think that this is kind of trivial, but actually entanglement plays a very important role. And this is true all these Gauss operators and these local symmetries. Actually, what you find out is that these spins, or these qubits, they have to, if you want to sense this Aharonov-Bohm interference, it's not enough if you put them in up states, or one of them up and the other one down, which would be the equivalent of a pi flux, because this does not respect gauge symmetry. In fact, what you have to initialize the system in is one of the 4 possible bell pairs. This is consistent with the parity of the Gauss law. So actually, what you find out is that now this system, it can be split into 4 levels, depending on which bell pair you are in. It can be this effectively zero flux state, where both qubits are lying parallel to each other, even in this psi plus, or phi plus, or phi minus. They are coupled through this tunneling. And in this tunneling, there is constructive interference, right? So they don't see any flux in between. So the phonon tunneling this way and the other one tunneling this way, they add up constructively. So I have 1 + 1 times the tunneling strength. Whereas if the particle is in one of these other psi bell states, where the qubits are lying antiparallel to each other, then one path interacts destructively with the other one. So there is actually no tunneling at all. So this is a pi flux, and there is a Aharonov-Bohm interference, which is now mediated by these links, which are dynamical. They were also able to prove this on the lab, because they are able to do entangling gates to prepare these states in different bell states. And actually what they found out is that when they initialize a single excitation in one of these center of mass modes and put the spins in a bell state where all the qubits are always parallel to each other, there is no effective gauge flux, right? So the particles, they can still tunnel periodically. And actually, the parity of this bell pair is constantly changing between phi plus to phi minus. This is what you measure here, because they can also measure correlations. So you see that this is correlated to the movement of particles. Whereas if you start it in the other bell pair, so up, down plus down, up, what you see is that there is destructive interference and there is no parity exchanges. So what you're seeing here on real time is this Aharonov-Bohm interference in play, right? Very good. So where can we go from there? And here I will be quite fast, but you can stop me at any point. So you can start now. So this part was more like looking at the fundamentals of these building blocks, and now you can start thinking about, in a Lego fashion, I have these building blocks, how I can glue them and go to models that are interesting from a many-body perspective, right? So this, I don't intend you to understand all these pictures here, but basically what I'm thinking about here is having these dimers that I was talking about today, that they hybridize into the center of mass mode, for instance, and I'm ordering them energetically so that I can start assisting these parametric drives in a zigzag fashion, so that at the end of the day I have a full 1D chain subjected to this gauge field. So this is the things of the plots that I was showing at the beginning that would allow me to show that I have 2 particles, and now these particles, they are confined. So this is one thing that they could do. Another thing that I find way more interesting is actually combining not just into this single C2 chain, which would be that one there, you start gluing together different loops, right? So I have now this loop where I told you that you can see Aharonov-Bohm interference through dynamical C2 fields, just one of these unit cells, and now I start gluing them together. So now you have a loop, what we call a C2 loop chain, and it has very nice physics. So the model is, again, this one is just 2 copies of this C2 chain, because now there are like all the possibility to tunnel over these gauge fields, or the possibility to tunnel over those, right? Each of the gauge fields is subjected to an electric field, and there might be the equivalent of the placket term in the C2 gauge theory, which was forces. Now it's just a weight to operator, right? It's just the interaction of C over here with C over there for each of the plackets. So that's nice, because this kind of interactions, they are physical. They could be implemented in the lab. And now we have a competition. So we have a competition on the one hand between the magnetic interactions and the electric fields. And on the other hand, we have a competition between the dynamics of the C2 charges and the electric and magnetic field, right? So it's a complicated model, and we want to understand a bit more what is the physics. There might be 0 or pi fluxes whenever this term is dominating, right? And what I know is that whenever the particles, they meet one of these pi fluxes over here or over there, they will not be able to tunnel, right? Because there is perfect interference. So this kind of fragments the system. It breaks the system into bunches. But whenever there is an electric field in the game, then essentially this electric field, what it can do is it can flip the sign of the, one of the qubits, which means that it brings me from a pi flux to a 0 flux, and then the tunneling is allowed again, right? So there is all this interplay, and actually we found out that this very nice physics that is related in a sense to caging phenomena, but now Aharonov-Bohm cages, but now these Aharonov-Bohm cages, they come from really dynamical gauge fields, right? So if you think about an analog of these dynamical gauge fields, just for in this field, well, maybe you don't know it, but you can think about going back again to gauge fields that are background. Here are dynamical, but here are background. So you see that in every plaquette of my system, I have a phi term that controls the flux, and now my particles, they can tunnel in this kind of diamond structure. Whenever the flux is pi, what you find out is that in this system, I can diagonalize this exactly, and for pi flux, you find that, pi flux over here or over there, you find that all the bands, they touch each other. Essentially, there are flat bands, right? And on top of that, there are peculiar states that live on the boundaries, which would be the ones that you see over here. These are these topological edge states. I want to focus on these points over here, because essentially what happens when you have flat bands is that everything is non-dispersive, so things remain very localized. And actually what you find out here is that for these pi fluxes, the destructive Aharonov-Bohm interference makes my particles, they are confined into cages that have a very small support. So we have the equivalent of that, but now in a system where these fluxes, they are dynamical. So we want to understand what is going on. This is very detailed, but what we found out actually is that the system can order itself into different layouts or configurations of these Aharonov-Bohm cages. So you can start thinking about adding a chemical potential, so going to finite densities, and now seeing how these particles will like to arrange themselves by minimizing the energy in this grand canonical ensemble, and how they do so by depending on the magnetic interaction, for instance. And what you find out is that there are regimes where all there is no Aharonov-Bohm fluxes at all. It's completely zero flux everywhere, and my particles, they can move freely. There is another regime where I put a pi flux every side, so nothing can move at all. But now there are some other more interesting regimes where I have like finite Aharonov-Bohm cages that break my system into pieces, and they order themselves forming like crystalline solutions that might have some periodicity, which might be 2, 3 or so, or the filling it can also vary. So in practice, what this means is that if I now go vary in the magnetic field, I will go from, and I'm in a certain filling, so I'm now in the canonical ensemble. I can go from phases which are fully connected to some other phases where energetically it's favorable to pin like pi fluxes and break my chain into smaller subpieces where the particles can tunnel with each other, right? So this is a new mechanism for confinement, because these particles over there, they cannot move away, so they are kind of confined within the Aharonov-Bohm cage, and it's in a regime where the magnetic field is dominating. So the previous regime of confinement was dominated by the electric field, now it's dominated by the magnetic field. So we explored this. I will not bore you too much with the details. I just want to tell you that, let's go to this. Let's go back to, first of all, the standard confinement regime. So I'm now in a particular regime where the electric field is much stronger than everything else. And therefore, what happens is that I put my particles, and whenever I put the particles, I generate a string that wants to be as small as possible, an electric field string that connects charges, and it wants to be as small as possible. So here, I have 1, 2, 3, 4, 5, 6 charges, and essentially, the string, it just connects them in the way that it's the shortest possible, right? What happens now when you add tunneling and you add magnetic field, where there can be fluctuations, right? So for instance, this particle over here, although it's energetically not favored, it can tunnel there virtually, right? It enlarges the string that goes this way, and then in a second process, this particle over here, it can tunnel to the neighboring site, so there is an effective tunneling. And this is a manifestation of this confinement. So my particles, they never arise on their own, they always arise in pairs, and these pairs, they're free to tunnel through this second order process, basically. So it's on the order of t squared divided by h. And if you calculate the correlator, you find out, in fact, that all single particle Green's functions, they are exponentially decaying, but these 2-point correlators that involve pairs of particles sitting together and linked by an electric field, it has a power law decay, and this means that these particles, they are free to move. So these are the mesons of my system. This is the standard picture. What we found out is that if you go to the other regime that is not dominated by the electric field, but is dominated by the magnetic interaction, actually exactly the same physics happens, but in a different regime. So now I have my 0 and pi fluxes. They inhibit the tunneling from one plaquette to the other. So for instance, I put 4 particles. They are inside Aharonov-Bohm cages over here, there, and there. And what can happen now, I'm in the regime that is dominated by the magnetic field interaction, and the tunneling, the electric field is very small, so it's perturbative. But now this electric field, what it can do is it can flip this phase to 0, right? So it allows my particle to delocalize. But this is energetically not favorable. So at second order, what will happen is that now I flip this flux to pi, and the particle is reconfined over here, right? So it's a different perturbative process, but the effective model is exactly the same. It's the model of a tight binding composite particle with longer range, well, not longer range, but not nearest neighbor, but next to next nearest neighbor interaction. And this is deconfined, and it has power law decay. We tested this through the correlators, but also by looking at entanglement entropy. So this probably for those of you that are familiar with that, if you have a system where you have free particles moving, this is a kind of a Luttinger liquid in 1D, then the entanglement entropy, it has a certain scaling with the length of your bipartition with respect to the total length of the system, and by fitting it, you extract something that is related to the underlying effective field theory that controls this excitation. So we proved that indeed these mesons, they follow a particular central charge of the field theory. And going back to the phase diagram, I was talking a lot about what happens when you change the coupling strength of this CC interaction, so this magnetic coupling strength, but you can start now playing with the electric field as well. So what we found out is that everything was gapless and is in this, confined regime where mesons can move apart, but actually there is a gapped phase which is related to the breakdown of translational invariance, and this you can see, essentially for 2/3 filling, there is a particular packing of these Aharonov-Bohm cages actually that they become fully packed and they cannot move at all. So there is a period 3 unit cell, so it's 0, 0 pi fluxes, and then you repeat. And this is a gap phase, so you cannot move it around, you cannot add particles, and actually the entanglement entropy looks very different from this conformal field theory prediction. It's actually just oscillating and reflecting the fact that these phases, they are kind of breaking translational invariance. How am I doing with time? 2 minutes. 10 minutes, okay. Yes, I think that I wanted to tell you a bit about a completely different model, but I think that this is too much. I'm tired of talking. I'm sure you're tired of listening. Just the idea is that you can start, I will not cover the details, but we were talking about this chains of C2 loops where the matter particles, they just live on the sides, but they just have 2 different options of tunneling to the neighboring one. Now you can be more complicated and think about really ladder structures where my particles, they live on 2 different legs. Here are the blue sides, and they can tunnel in within each leg mediated by a C2 gauge field, but there are also interleg tunnelings or cross-link tunnelings. So this is a very nice structure that was put forth in lattice field theories to discretize fermions and to deal with the fermion doubling, but now here we are gauging the links, so there is like a full gauge theory. And what we found out is that this Aharonov interference, it manifests also not through these Aharonov-Bohm cages, but through something that we call Aharonov-Bohm instability, and is related to, in a sense, to the Peierls instability. So if the flux is 0, so if all the spins, they lie parallel to each other in one of these rectangular plaquettes, essentially I have a gapless system. There are 2 bands, but they cross each other. Whereas if there is a pi flux, there is this perfect Aharonov interference, and suddenly I have 2 flat bands that are disconnected with each other. And this is energetically favorable, so the system itself, it wants to go to a pi flux phase. So we found out that there's a nice interplay with topology. So there's a region in phase space with these pi flags also develop set states and SPT order. And actually, we found out also that this is a topologically ordered phase. So essentially, you can think about it as well. This maybe too much. Well, let's just leave it this way. So you can think about this ladder as if it was a cylinder. And actually, what you find out is that in the regime that is dominated by these pi flags, there is a degeneracy in the ground state. So the ground state can be either all these pi flags around, but it can actually have a flux that goes inside a cylinder, right, or not. So there are like a twofold degenerate ground state that contains what people in condensed matter call a boson thread in the cylinder. And actually, the fact that we have a cylinder is only due to the fact that these cross tunnelings actually, so I can connect the upper leg to the lower leg through either this tunneling, but I can also connect it through this other one, right? So if you think about like blowing this connectivity, you can go from the upper leg to the lower leg, either going this way, right, through one of these tunnelings, or you could go the other way through the other tunneling, right? So there are like this kind of, the connectivity in this lattice actually is telling you that what you have below when you gauge it is like a cylinder, and these cylinders, they have non-contractible loops around the cylinder that allow you to have this degeneracy, which is related to topological order. We found solitones and some other things, but I think I will stop here. And the last message I want to bring is that we might be, for many, many years, very far away from this QCD and large-scale gauge theories, but I think that by looking into these problems from a different perspective, we can bring like very nice physics into the game and actually see them, some of them in the lab. Thank you very much.
Thanks for the nice talk, Alejandro. Now it's time for question and discussion. Do you have any question? No? Okay, I have one. Maybe it's a bit off topic because you mentioned all of the thing about gauge theories, and it's more related about gravity. So can you implement like a non-Euclidean metric in this context of trapped ions with vibrational modes and so on? And if so, how can it be implemented? Like, which terms do you have to add to the Hamiltonian? And
what do you mean, like non-Euclidean?
I mean, a curved space-time, or yeah.
I see. Okay, so like some Riemann. Yeah. So in fact, what you can think about is the equivalent of, for instance, what I was talking about, these background gauge fields. You could think about having background gravitational fields, so like a background metric. Mm-hmm. It's not very clear to me how you do in these analog simulations to give dynamics to, like fully dynamics to the metric and to make like a, a full gravitational theory where you have a field that responds to the metric, and the metric fields the back action of the field, right? But what you can do for sure, and there are many papers on that, is to simulate the physics of massive particles reacting under this background metric. So this, in fact, Carlos Fulgado has some papers on that, not on trapped ions, but on ultra cold atoms in optical lattices. And at the end of the day, when you think about the problem is kind of similar. So for instance, the background gauge field here, what it does is it adds a phase to the tunneling strength. What you could think about is if now you make this tunneling strength inhomogeneous, and this inhomogeneity, is according to some prescribed discretization of your field theory in the curved space-time, then you're making like a simulator of that. Or if you're interested in cosmological settings where maybe your metric is not curved especially, but just evolves in time, then it's even simpler because it's just some of the parameters in your discretized field theory, they have to be tuned in time according to a certain prescription. Okay. So yeah, I think that, and if you do this with trapped ions, I think it will be very similar to what we discussed for cold atoms. It's just finding the right scheme to incorporate these time dependencies or these inhomogeneities. Okay.
Thank you so much. Are there any more questions?
Thank you for the talk. Could you please repeat how you couple the phonons with the laser? Because as long as I understood, the phonons have no electric charge. So at the beginning of the
That's
talk.
right, yes. So yeah, so maybe what I can do is so essentially here. So typically the idea is very similar. The details are different, but anyway. So you might these are my two internal states, right? And now what you can do is that you can shine a laser, right, that excites one of those, right, from the down spin to the up spin. And this is controlled by the right frequency of the laser, which at the end of the day is just the dipole element, right? This would be the electronic position in your outer electron in your ion, right? It couples to the electric field of your laser, and it induces a transition and then probably right? So this is the rabbit frequency. And now the idea is that on top of that, actually this would be like the electric field amplitude that the laser is like a plane wave, right? Where now so it not only couples to internal states, but actually the wave vector of the laser it can recoil in the motion of the charged particle, right? So what you can imagine is that on top of having these internal states, actually what you have is like a whole finer structure of vibrational levels, right? And the idea is that these vibrational levels are inbuilt here. So R is now the position of the ion, not that of the electron. So it will be some equilibrium position, but then you will have some normal modes which go from 1 to n, capital N, and this will be, whatever distribution of the vibrations of the ions. But then it has like the creation and annihilation operators of the phonons, basically. You have to divide properly by the mass of the ion and the frequency of the mode, and probably I can see here also the phase. So you see that the phonons, they appear here, and they depend on how the recoil of the laser couples to the vibrations, right? So this also carries with, some direction, some axis. So these are the vibrations of the ion that create a phonon in mode n, but also along the direction alpha. So what you do now is, instead of setting the laser frequency to be exactly that of the energy difference between the qubit up and qubit down, what you do is that you detune it a bit, and you go to what people call sidebands. So for instance, you detune it, and you go to the vibrational direction omega x. That means that every time the atom is excited, it goes from spin down and 0 vibrational excitations to a spin up and 1 vibrational excitation. Right? So it will be 0 and it will be 1. So by detuning the laser, you're actually coupling the internal state to the motion. And this you can do in several fashions. So this one, what it would do when you do this is essentially an interaction that does something like that. It's called a blue sideband. You can do another interaction by controlling the frequency that is something like that. This would be a red sideband. But what you can actually do is also an interaction where instead of coming with a single laser beam, now you come with two. So with one you excite it virtually, and with the other one you come down, and what you can create are interactions that are something like this. Right? The only thing that you are missing now, out of this exponential of all the creation and annihilation operators, these are the linear terms. phonon tunnels from mode I to mode X, and this is negated by the QT. So this is what allows you to play with all these invariant functions.
Are there more questions? If not, let's thank Alejandro again. We still have like a couple of minutes, so I think it's a great time to take the group picture. So let's go to the La Casa de Papel, this central building of the SIG, and let's take the group picture.